A star is not a fragile thing. Our sun has been burning for approximately 4.6 billion years. It will burn for approximately another 5 billion. It survives by balancing two forces that would individually destroy it: the gravitational pressure of its own mass pulling inward, and the radiation pressure of nuclear fusion pushing outward. These forces have been in equilibrium for longer than the Earth has existed. The Sun is 1.4 million kilometers across. It contains 99.86% of all the mass in the solar system. Its surface temperature is 5,500 degrees Celsius. Its core temperature is 15 million degrees Celsius. It converts 4 million tons of mass into energy every second through nuclear fusion, and has done so continuously for 4.6 billion years without interruption. A star is not a fragile thing. Now let's talk about what happens when one gets too close to a black hole. The process has a name. Astronomers call it a tidal disruption event. The name is precise and clinical and communicates almost nothing about what actually happens. What actually happens is this: gravity is not uniform. It follows an inverse square law. The closer you are to a massive object, the stronger the gravitational pull. This means that if you are near a very massive object, the gravitational force on the side of you facing the object is significantly stronger than the gravitational force on the side facing away. This difference, the gradient of gravitational force across an extended object, is called a tidal force. The moon's tidal force on Earth is what causes ocean tides. The difference in gravitational pull between the ocean facing the moon and the ocean facing away from the moon is small enough that the result is a gentle rise and fall of water level. Near a black hole, the tidal force is not gentle. The point at which tidal forces become strong enough to overcome the internal gravitational cohesion of an object, the point at which the gradient of gravity across the object exceeds the object's own ability to hold itself together, is called the Roche limit. Named after the French astronomer Édouard Roche, who calculated it in 1848 for rigid and fluid bodies orbiting a more massive object. For a star approaching a supermassive black hole, the Roche limit is the point of no return. Not because the star cannot escape gravitationally, it might still be outside the event horizon, still technically able to move away, but because at the Roche limit, the tidal forces exceed the star's self-gravity. The star does not fall into the black hole. The black hole reaches out and pulls the star apart. Let's go through what that looks like. Because the mechanics of a tidal disruption event are stranger than the summary suggests. As a star approaches a supermassive black hole on a close orbital trajectory, drawn in by a chance gravitational interaction that altered its path over thousands of years, it begins to distort. The side facing the black hole is pulled harder than the side facing away. The star stretches. Its spherical shape elongates into an ellipsoid, then into something that no longer resembles a star at all. This stretching happens while the star is still hundreds of millions of kilometers from the event horizon. The black hole does not need to swallow the star to destroy it. It only needs to get close enough that the tidal gradient exceeds the star's structural integrity. At the Roche limit, the star ceases to exist as a coherent object. What had been a sphere of plasma held together by its own gravity for billions of years becomes, in a matter of hours, a stream of gas. A long, thin ribbon of stellar material, billions of tons of plasma, stretched along the orbital path. This stream, called a tidal stream, wraps around the black hole. Approximately half of the stellar material is gravitationally bound to the black hole and falls inward. The other half is ejected outward at high velocity, flung away from the system entirely. The bound half does not fall directly into the black hole. It forms an accretion disk, a swirling structure of superheated plasma orbiting the black hole at relativistic speeds, gradually spiraling inward as angular momentum is transferred outward through friction and magnetic interactions. As the material falls inward, it heats to temperatures exceeding tens of millions of degrees. It emits radiation across the entire electromagnetic spectrum: radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays. For weeks to months, a tidal disruption event can outshine the entire galaxy it occurs in. A galaxy containing hundreds of billions of stars, outshone by the death of one. The first tidal disruption event was not observed directly. It was inferred. In the early 1990s, the ROSAT X-ray satellite detected luminous X-ray flares from the centers of several otherwise inactive galaxies. Galaxies that had no ongoing star formation, no active nucleus, no reason to be producing X-ray emission at those levels. The flares rose rapidly, peaked, and then declined over months to years in a pattern that matched theoretical predictions for material falling onto a supermassive black hole. The interpretation that these were stars being disrupted and consumed was proposed but remained contested. A star being torn apart by a black hole was theoretically predicted but had never been confirmed observationally. In 2015, that changed. On November 11, 2014, the Intermediate Palomar Transient Factory detected a brightening in a galaxy approximately 290 million light-years away. The source was designated ASA SSN-14LI, named after the all-sky automated survey for supernovae that confirmed it. Over the following months, it was observed across multiple wavelengths. The light curve, the spectral signatures, the X-ray emission, everything matched the theoretical prediction for a tidal disruption event. A star, approximately the mass of our Sun, had passed too close to a supermassive black hole containing approximately 10 million solar masses. It had been stretched, torn apart, and was now being consumed over the course of months. The light reaching Earth in late 2014 and 2015 had left that galaxy 290 million years ago, while complex multicellular life was first establishing itself on Earth's land surface. The star died 290 million years before anything on Earth was capable of noticing. Now let's talk about the part that changes the scale of this. In 2018, a tidal disruption event designated AT2018 COW was detected in a galaxy approximately 200 million light-years away. It was bright enough to be initially mistaken for a supernova within our own galaxy. A T2018 COW, nicknamed the Cow by astronomers after the random letter sequence in its designation, brightened to peak luminosity in approximately 2 days. Standard tidal disruption events take weeks. The Cow took 2 days. Its peak luminosity was approximately 100 times brighter than a typical supernova. It produced X-ray and radio emission at levels that current models of tidal disruption events struggled to explain. The mechanism driving the extreme brightness and the extremely rapid rise time remains debated. In 2022, an event designated a T2022 CMC was detected at a distance of approximately 8.5 billion light-years, more than halfway across the observable universe. It was producing a relativistic jet, a beam of material moving at 99.99% of the speed of light, aimed, by chance geometry, toward Earth. The jet made it visible at a distance at which it otherwise would not have been detectable, 8.5 billion light-years, a relativistic jet from a star being torn apart, detectable from halfway across the observable universe because the geometry of the destruction happened to point toward us. The jet was not aimed at Earth in any meaningful sense. It was aimed in our direction. The distance made impact impossible, but the geometry, the reminder that these events produce directed beams of energy at relativistic velocities, is worth sitting with. A tidal disruption event in our galaxy producing a relativistic jet aimed at Earth at a distance of a few thousand light-years would be a different calculation entirely. Here is what current data says about that possibility. Tidal disruption events are estimated to occur at a rate of approximately 1 per 10,000 to 100,000 years per galaxy. Our galaxy, the Milky Way, has a supermassive black hole at its center, designated Sagittarius A star, with a mass of approximately 4 million solar masses. Sagittarius A star is currently quiet. It is not actively accreting significant amounts of material. It produces occasional flares, brief brightenings detectable in X-ray, but nothing approaching the sustained luminosity of an active tidal disruption event. The center of the Milky Way is approximately 26,000 light-years from Earth. For a tidal disruption event at that distance to produce dangerous radiation levels at Earth, it would need to produce a relativistic jet aimed in our direction, and jets are not produced by all tidal disruption events. Estimates suggest approximately 1% of tidal disruption events produce detectable jets. The probability of a tidal disruption event at Sagittarius A star producing a jet aimed at Earth in any given human lifetime is extremely small. Extremely small is not zero, and the universe contains approximately 2 trillion galaxies, each with a supermassive black hole at its center, each producing tidal disruption events at the estimated rate. Across the observable universe, a tidal disruption event is occurring somewhere approximately every few seconds. Every few seconds. Somewhere, a star that has existed for billions of years, a star that has survived longer than life has existed on Earth, is being stretched, torn apart, and consumed in a process that briefly outshines entire galaxies. Every few seconds. Let's return to where we started. A star is not a fragile thing. It is 1.4 million kilometers across. It converts 4 million tons of mass into energy every second. It has maintained the same fundamental structure for billions of years against the constant inward pull of its own gravity. And in the presence of a sufficiently massive black hole at sufficiently close range, none of that matters. The tidal force does not negotiate with fusion pressure. It does not care about the star's temperature, or mass, or age, or luminosity. It applies a gradient of gravity across the star's diameter, and if that gradient exceeds the star's self-gravity, the outcome is the same regardless of how long the star has been burning. Hours. The process takes hours. A star that took millions of years to form, that has burned for billions of years, that contains more mass than 1 million Earths, reduced to a stream of plasma in hours. Half of that plasma falls inward and is consumed. The other half is ejected into intergalactic space, stellar material that will drift through the void for billions of years, too dispersed to form new stars, too thin to condense into anything. The remnant of a star, scattered across a volume of space too large to ever reassemble. The black hole continues, unchanged, slightly more massive, patient in the way that objects with no consciousness can be said to be patient, which is to say, indefinitely. The star is gone. The black hole does not notice. Your question: if Sagittarius A star, our galaxy's central black hole, 26,000 light-years away, underwent a tidal disruption event tomorrow, producing a relativistic jet, and that jet was aimed at Earth, how long would we have between detection and arrival? Work it out before you answer. The numbers are in this video. Drop your answer in the comments. Next video: the planets that were ejected from their solar systems and now drift through interstellar space with no star, no light, and no heat source, and what the evidence suggests about how many of them there are. See you there.